Ladies and gentlemen, thank you for watching this video. My name is Adria Mallol from the University of Augsburg, and today I will introduce our paper entitled The Filtering Effect of Face Masks in the Detection from Speech. This is a research question that we wanted to investigate in this work. How can we better assist computers to detect when a speaker wears a face mask? For this, we focus on two main aspects. The first one is that face masks attenuate frequencies above 1 kHz. And to resolve this research question, we compare a paralinguistics and a spectrograms-based approach. Before going any further, let me introduce my co-authors, Shuo Liu and Professor Björn Schuller. This is the agenda for today's talk. I will start with a brief introduction, then I will present the dataset used in this work. I will describe the methodology followed and the experimental results obtained, and I will finalize my talk with some conclusions. COVID-19 spreads via respiratory droplets among people in close contact when coughing, sneezing, speaking, singing, or when breathing heavily. To control the spread of the virus, governments have ruled on the obligatoriness of wearing face masks in public transports, in public spaces, in frequented streets, in shops, or even in workplaces. Therefore, there has been the need to check the compliance with this precaution measure. For this, researchers have investigated new digital solutions for the automatic detection of face masks, either from the analysis of visual information or from the analysis of acoustic information. To justify our research, face mask materials give them specific properties in terms of thickness and porosity, which cause the absorption of frequency content. This is how we can explain that face masks act as filters to the human voice. What we can see or what we can hear actually is that when we wear a face mask, our voice changes slightly. This is because the frequencies above 1 kHz are attenuated. Therefore, our hypothesis is that the exploitation of the frequency content above this cutoff frequency should be more discriminative for the task at hand. In this work, we used the Mask Augsburg speech corpus, which was released as part of the InterSpeech 2020 Compare Challenge, and it provides data recorded at 16 kilohertz from 32 German native speakers, 16 females, 16 males, and the dataset contains more than 10 hours of data. The original audio files were segmented into frames of 1 second length, and here you can see a table summarizing the total number of segments available in the 3 different partitions of the dataset. So as you can see, more than 36,000 samples were available in total. When we started working with dataset, we wanted to do a preliminary investigation in order to check whether we could see the absorption of frequency content above 1 kHz. So here I show you a couple of examples of spectrograms. The two examples or the two spectrograms on the left-hand side belong to a female participant. The two spectrograms on the right-hand side correspond to samples from a male participant. And those on the left correspond to a sample without wearing a face mask, and those on the right while the participants were wearing a face mask. Therefore, if we pay a little bit of attention to the frequency content above 1 kHz, we can see that when the participants were wearing a face mask, there are less energies in the spectrum. Therefore, we believe that this kind of frequency should be reasonable and suitable to perform our experiments. So we focus this work on comparing two different approaches. First, the paralinguistics-based approach, and then a spectrograms-based approach. For the linguistic-based approach, we work with the original, the low-pass, and the high-pass versions of the audio signals. To generate the low-pass and the high-pass versions, we used dedicated low-pass and high-pass 20th order Butterworth filters. Then with these 3 audio signals, we extracted their paralinguistic features using OpenSmile, and in this case, we focus on using the compare feature set, which provide more than 6,000 features. As you can see, this is a very large feature set, and we decided to apply dimensionality reduction using PCA, so we just kept 90% of the variance for our experiments. To modeling these features, we compare two different techniques. First, a standard supervector machine, and then a multi-layer perceptron. This MLP was implemented with 3 fully connected layers with 64, 16, and 1 neurons respectively. And the first 2 layers of this MLP use the rectifier linear unit as the activation function, and the last layer use the sigmoid as the activation function. Moving forward to the spectrum-based approach, in this case, we investigated or we exploited the spectrum representations of the audio samples. Specifically, we created 3 different sets of spectrograms. The first set were the original spectrograms, which contain all the frequencies available from 0 to 8 kilohertz. Then we created a subset of the spectrograms focusing only on those frequencies below 1 kilohertz, and another set of spectrograms only containing the frequencies above 1 kilohertz. These spectrograms were stored as images of 256 times 256 pixels for further processing. Also, the spectrogram representations visually change a lot when we use a linear or the logarithmic frequency scale. Therefore, we generated both spectrograms in order to compare their performances. In this case, to model this information, we use the combination of a convolutional neural network followed by a multi-layer perceptron. For the CNN, we implemented 2 convolutional blocks with 6 and 16 channels respectively, and for the MLP, we used the same structure as in the paralinguistics-based approach for a fair comparison between both approaches. So moving to the experimental results, we assessed the performance of our models using the weighted average recall, because this was the metric used in the challenge, and therefore we followed the same metric for comparison purposes. Here in this table, you can see a summary of the results obtained using the paralinguistics-based approach. And what we observe is that the best performances of around 67% of unweighted average recall were obtained using the high-pass filtered versions of the signals. Moving to the spectrums-based approach, what we can observe is that the models that obtained the best performances were those that exploited the spectrograms with the frequencies below 1 kilohertz. Also, if you compare the performances using the linear and the logarithmic frequency scale, you can see that the logarithmic spectrograms outperform the linear ones. We believe that this is because of the different distribution of the frequencies in the different bins of the spectrogram. I would like to conclude my talk with a couple of main ideas. The first one is that from the analysis of the paralinguistic features, we have observed that the high-pass filtered version of the speech signals contained more salient information for the task, and this result supported our hypothesis. Also, when analyzing the spectrogram representations, what we observe is that the spectrograms with frequency content below 1 kilohertz achieve the best unweighted average scores. Therefore, it seems reasonable in this case to state that phase masks impact the energy of the low frequencies in the spectrograms. To summarize my talk, I would like to finish with a couple of take-home messages for you. The first one is that phase masks alter the frequencies above 1 kilohertz in such a way that it's detectable with paralinguistic features. The second one is that phase masks impact the energies of the frequencies below 1 kilohertz in the spectrogram in such a way that is detectable with convolutional neural networks. Thank you for your attention.